Welcome back to Multigrid Methods. Today we're starting Chapter 10. It's going to be Chapter 11 in the notes that you find on Canvas for those of you who are local. That's because we injected a new Chapter 2 into the notes, and so things got shifted by one. But for those of you who only have the slides, it's Chapter 10. And Chapter 10 is all about convex optimization. And the reason why we're going to study convex optimization is because we're interested in applying multigrid solvers to do optimization. And this is kind of a modern topic, and optimization is kind of everywhere. We're going to focus on things that are well suited to the multigrid method. That is, optimization problems that are well suited to that, and those problems are ones which are by nature convex. Now, if you work in machine learning, you may have heard a lot of talk about non-convex optimization or optimization for functions that have multiple local minima and things like that. In machine learning and things like that, um, in high dimensional approximation theory, where you're trying to fit a function to a complicated set of data, things are not always convex, and the problems become a whole lot more complicated. And so we won't be able to address those complications here, but we will be able to talk about maybe what it's like if you're in or near a local minimum and you want to run a solver to find the exact point of local minimum. In those little basins, the things tend to be convex. That's because we can look at the function that we're trying to optimize as being something approximating a quadratic functional. In any case, so convex optimization, this is kind of where we leave the world of mostly matrix-based approach that we were using for, you can see the title of the book is a mostly matrix-based approach. And the reason why I had to say a mostly matrix-based approach is, well, originally it was an entirely matrix-based approach until I decided to add this bit on convex optimization. And then we need to look at things from the lens of Banach spaces and Hilbert spaces, and things get a little bit more complicated than just finite dimensions and matrices and things like that. All right, so this is going to be a part one, a slide deck one of two. So I plan to cover the first two sections of chapter 10 in this slide deck, and then the second two in the second. There are only four sections, at least at the moment, in chapter 10, so that should work out for us. So the purpose of this chapter is to present some background information regarding basic linear functional analysis, stuff that you may have seen in a course on applied linear analysis. And some of you are taking functional analysis now, and so you know a lot more about this than even I do. We're going to talk about convex functions and their minimization. When you talk about convex functions and their minimization over Hilbert spaces, then you have to necessarily think about and talk about functional analysis. So we're going to deviate significantly, as I said, from our mostly matrix-based approach that we've been using so far. And that's because, as I said, we're going to need to equip ourselves with some machinery and terminology from the worlds of Banach spaces and Hilbert spaces. Now, the convex optimization that we're going to do is going to be based on something called subspace decompositions. So we're going to break space up into subspaces, and this is a little bit like breaking a grid up into pieces, or breaking up, thinking about a grid as being structured in some sort of multi-level way. So this is how optimization is ultimately going to relate to the multigrid method. All right, so let's talk about first in this first section, analysis on vector spaces. So I'm going to refer a lot of our proofs to this book by C.R. Lay from 2013. It's a nice SciAm book that many of you have seen. It's basically a book on linear functional analysis. Well, it has some nonlinear functional analysis in there as well. And so a lot of the proofs in here will be different than what we've seen previously because there won't be an exercise referenced, and I'm not going to give the proof, and I'm not going to ask you to give the proof because it's understood to be or require a bit more depth than what we're going to have in this course. But all the facts that I state are going to be true, and you can look up the proofs if you're so inclined to do so. So a Banach space is a pair of things, objects. One is a set, and that is a linear space. That is, it's a vector space. I can add uh, objects from the space together. I can make arbitrary linear combinations, actually, of objects in the space, as long as they're a finite in size. Linear combinations finite in size. And this object here is a norm. So norm is something we've seen on finite dimensions before. We've used those a lot in the course, and so it would behoove you to know what are the properties of a norm. For example, you need to know the positivity property of a norm, the triangle inequality property of a norm, etc. So if I equip this with a norm, then it's called a normed space. Okay. If the space is complete, meaning that every Cauchy sequence is a convergent sequence with respect to that norm, then we say that the normed linear space is actually a Banach space. If in addition, we know that it's a Banach space and the norm is generated by an inner product, then we call this space a Hilbert space. So you all have seen this, especially those of you who have taken functional analysis and or applied linear analysis. I know that many of you took that course with me, which here at the University of Tennessee is numbered 547. So let's get into an example right away. Suppose that we're considering Rn for n being some positive integer. Suppose that p is any number between 1 and infinity, inclusive of 1 and infinity. And we're going to define a norm on this space. We're going to, in particular, define what's called the p norm. So if p is between 1 and infinity, not inclusive of infinity, then the way to do that is to sum from 1 to n vi absolute value raised to the p power. Now, here if this is the complex vector space of dimension n, then this would be the modulus. And here it's just the absolute value. We don't need anything fancier than absolute value. But as I said, if they're complex numbers, then this becomes the modulus. Absolute value raised to the p power, and then we're going to take that sum and we're going to take the pth root of that. Okay, take the 1 over p power of that. That's going to give us what's called the p norms. And so the common ones are the 1 norm and the 2 norm, and not so common are things like 3 and the 4 norm, etc. But if p is equal to infinity, then we're going to take the maximum in absolute value of vi. And well, how is this related to this? Because we've given it the same symbol. Well, it turns out actually if if we send or take a limit as p goes to infinity, then this object is going to pop out as the value for the p norm. Okay, so in some sense, the infinity limit is the limit of that guy, and so that's why it's called the infinity norm. For every p in this range, this is a Banach space. In addition, whenever p is equal to 2, this norm is generated by an inner product. It becomes the Euclidean norm in this case. And in this case, this space, this Rn equipped with this metric becomes what's called a Hilbert space. Okay, so a Banach space for every p, and a Hilbert space whenever p is equal to 2. That's the special case. Now, in finite dimensions, it's well known that all norms are equivalent. That means if I have a finite dimensional vector space like Rn, there's some constants. If we have, say, 2 norms lying around, let's call it the circle 1 norm and the circle 2 norm. Now, this doesn't mean the 1 norm or the 2 norm. These are just 2 different norms. Then there are constants that are independent of V, such that a relation like this holds. Okay, so there exists C1, C2, such that this holds for all V. So this is what we mean when we say that norms are equivalent. Now, in finite dimensional spaces, all norms are equivalent. So if you generate any norm, as long as it satisfies all the good properties of a norm, then we can easily show that that norm is going to be equivalent to any other norm that you might want to build. So that's a kind of interesting fact. And so, by the way, that means that Rn with any norm that you want to put on it whatsoever is going to be a Banach space. All right. And Rn with any norm that's good and true whatsoever is going to be a Banach space. It also means that actually, since Rn is isometrically, or let's see, isometric at least, to a finite dimensional, let's say it this way, a finite dimensional vector space is isometric to Rn for some n, as long as it's a real vector space, and that's all we're going to consider here. And therefore, we can say with certainty that every finite dimensional vector space is complete under any norm that we want to choose, as long as it's a good and true norm. So here's an example that shows that in infinite dimensional spaces, the choice of the norm matters. Okay, in infinite dimensional spaces, the choice of the norm matters. So I had better come up with an infinite dimensional space to make this case. And so the one I'm going to use is the space of continuous functions on some set omega over bar. That means the closure of omega in some in RD for some D. So, right, the continuous functions on that space. What this means is the continuous functions that are real valued. And so if I need to make a distinction ever, then the way you make the distinction is you put the range, it's the second object in the symbol. So this could be real. I could put the complex numbers here. I could put Z here, something like that, right? But if I don't write anything, then this is understood to be real valued. All right, so what about this object here? So this turns out to be a good and true norm on this space of continuous functions on the closed domain. It's called the L2 norm, or the 2 norm sometimes. And it's gotten by taking the function, squaring it pointwise, and then integrating that over this bounded domain omega. Okay, well, yeah. So the fact that I have an absolute value here is not necessary because I'm squaring a function, and the square of the function is the same as the square of the absolute value. Okay. If this was a complex number, then that wouldn't be true. I really would have to take the modulus and square it. In any case, we're in real land, so we square this function and we integrate it, and then we're going to take the square root of that. And that gives us a norm. In fact, it's a norm that arises from an inner product called the L2 inner product, which you probably know and have seen. However, if I norm the space in this way, this space turns out not to be complete. If I come up with a Cauchy sequence in this norm, that Cauchy sequence doesn't have to converge to a function in this space. In fact, I can show, for example, that I can converge to functions which have point discontinuities. And so that means the limit point of a sequence is not necessarily back in the space. That's a problem if you want this to be a Hilbert or a Hilbert space, I guess, in this case. Now, if I swap this norm out for another norm, I might get lucky. And in fact, if I use the L infinity norm, which is defined as the supremum taken over all x in the closure of omega of absolute value of f of x, then this norm, the L infinity norm, makes this space complete. So not every norm that you equip or that you pair with a set, a vector space, makes that a complete vector space or complete normed linear space. Not every norm that I equip with this space makes it into a Hilbert or a Banach space. So this guide is a norm, but it's not a norm that comes from an inner product. So the object that I create by pairing this norm with this is purely a Banach space, is not a Hilbert space, but at least it's complete. Every Cauchy sequence is going to have a limit point. It's going to be a convergent sequence, and that limit point is going to exist back in this space. You probably learned this from your 400 level, your senior level analysis course, and it goes a bit like this. The uniform limit of continuous functions is continuous. So that's the way I always learned it. The uniform limit of continuous functions is a continuous function. So that's that theorem which we're applying to show that that's complete. Well, it's related to that. All right, so if it's clear from the context, we're going to refer to a Banach and Hilbert space simply by naming the vector space, and we won't necessarily add the norm or the inner product associated to it. Like, for example, commonly when I refer to this space, I'll say just the space, and it'll be understood that it'll always be paired with this inner product or this norm. That's a fairly common notion in functional analysis. It's a little bit sloppy though, and I tend to want to always, my knee-jerk reaction is usually to identify the norm that's coming along with that space. But in any case, oftentimes it's clear from the context and we don't have to do it. Now, there is another space that those of you who have taken measure theory have seen before, and that's called the Lebesgue integrable square integrable space, or L2 space. And that space paired with this norm becomes a Banach space, and in fact, a Hilbert space. But L2 functions, you know, are not quite continuous functions. They're a lot rougher. All right. So we're going to consider mappings between spaces. And so there's a special class of mappings that we want to consider. Let X and Y be norm spaces, the collection of all mappings with the domain X and the range Y that are both linear and continuous is denoted by this space. So they have to be both linear and continuous. So I don't have to tell you what a linear mapping is, and I shouldn't have to tell you what a continuous mapping is. Anyone who knows a little bit about real analysis knows what it means to be continuous from one space to another. But if you don't, I can remind you that a continuous space, sorry, a continuous mapping is one which is continuous, meaning that the inverse image of open sets is open, right? So that's one definition. There's also a limit definition of continuity. And so that one makes sense in this case because, you know, these are two norm spaces. And so there's a concept of limit given by the norm topology. When I say norm topology, I really mean the norm is the way that whatever norm is given on those spaces is the way we use to define what are called open sets. Okay, and as soon as you can define an open set, then you know what is the topology of a. So you know open sets, you know closed sets, you know that a certain collection of open sets is still open, blah blah blah, the usual stuff for topology. Right. So the continuity is the continuity in that topological sense or that limit sense. A function on X, a functional, sorry, on X is a mapping from X into R. We're going to be interested in a lot of cases, we're going to be interested in the collection of all linear functionals, or even the bounded linear functions, or sorry, I should say at this moment, continuous linear functions. And those are a special class of functions. But right now, a functional doesn't have to be a linear mapping from X to R. A functional is any mapping from X to R. But a linear functional and functional and the heart of functional analysis is this thing called a linear continuous functional is a special thing. So that one gets a special name. So if I have a Banach space X, then the space X prime is the space of all linear mappings, linear and continuous mappings from X into R. And that has a special name. It's called the dual space of X. X prime is what we call the dual space of X, and that's defined as the set or the really the space, it turns out, of all linear mappings from X into R. Okay. Well, I keep forgetting to say linear and continuous, but L, the symbol L seems to suggest that they're linear only, but they are linear and continuous both. All right. So the following result details some important properties of continuous linear mappings that I want to emphasize. The proof of this is not very hard, actually. It's kind of straightforward and is left as an exercise. Um, this is one of those very first things that you learn in functional analysis, actually. This equivalence that I'm about to name, and it just requires that you use the definitions. So let X and Y be normed linear spaces. Let T be a linear mapping. The following are equivalent. Okay. T is a bounded linear mapping from X to Y. T is continuous at 0. That is, for every sequence in X that converges to 0, and converging means in the norm, okay, such that Vn converges to 0 in the norm of X, then Tvn has to converge to 0. Okay, it's continuous at 0. All right. So right. So and that this convergence here has to be in the norm topology of Y. And the final thing is the mapping T has to be bounded. Okay, it maps, in other words, bounded sets in X to bounded sets in Y. In other words, there's a constant M greater than 0, such that for every V in X, TV measured in Y, remember T maps V into the Y space, so we have to take the Y norm on TV, and that's less than M times the original norm of V with respect to this X norm. Okay, so this is what we mean by bounded. So these three things are entirely equivalent. Okay, so being bounded is essentially just the same as being continuous for linear maps. Bounded and continuous are the same thing. So that's the important takeaway from this result. Now, the next important thing that we come to is something called the induced norm. And this is the same as the thing called the operator norm. And it's familiar to those of us who have taken numerical analysis and even functional analysis and a good course in linear analysis. It's the same thing essentially as the matrix norm. Okay, the matrix operator norm. Let X and Y be norm spaces. Doesn't have to be Banach spaces yet. Just norm spaces is fine. Suppose that T is a linear mapping, continuous linear mapping from X to Y. The quantity or the object that we're defining here, this is called the operator norm of T, is equal to the supremum of V over X, but not equal to 0. We can't take v as 0 yet, because that would make the denominator 0 identically by a property of norm. Remember, the norm of 0 is 0. In fact, that's the only vector that has norm 0. So it's going to be the supremum over v of the quotient tv in y over v in x. TV norm, or yeah, so say the y norm of TV over the x norm of v. This is called the induced or operator norm. And so it turns out that this object satisfies all the properties or characteristics of norm. And so you can go through each one, right? The positivity property, the positive definiteness property, the positive homogeneity property, and then finally the triangle inequality property. So those are the things that you have to check. Now, for the special case that T is a bounded linear bounded linear functional. So the dual space is the space of all bounded linear functionals. So I'll commonly say if T is a bounded linear functional, then the operator norm simply rewrites like this. So the main difference here is that if we're mapping into R, the natural metric on R is just the absolute value symbol. So I can replace the norm on the Y norm on TV, which is the absolute value, because this object here is just a real number. So we get a nice simplification of things whenever T is a bounded linear functional. All right, so now here's a very nice property that, well, a couple of nice properties. The first one is, suppose that X and Y are norm spaces, then this space, the space of bounded linear functionals or bounded linear operators from X to Y, turns out to be a vector space. That is, I can make linear combinations of bounded linear operators and I can get another bounded linear operator, right? So how would I do that? So if I have one bounded linear operator, L, and that takes me into into Y, right? And I have another one that does the same thing, right? For each Y or for each U, I guess. So I can add these or make a linear combination of these two things, right? And the natural way to do that is alpha L1U plus beta L2U is how we define a new linear operator called alpha L1 plus beta L2, which acts on U, right? So if I define this object this way, this new bounded linear operator, I'm going to add them together in this way. And this thing here is a bounded linear operator. Okay, it's very easy to show that. You just check the various properties. So that means that if I add two of these together, I get something back in the space. So this has to be a vector space. Now, I've already given a norm, a possible norm on this vector space, because I've shown you how to compute something like this. So this object that I just defined is actually a bona fide norm. Okay, the induced norm, the operator norm, is a true, good and true norm on this space of functions. And additionally, if Y is a Banach space, only need Y to be the Banach space, then this whole space is a Banach space under the induced norm. Okay, X doesn't even have to be a Banach space. It could just be a normed vector space, a normed linear space. If Y is a Banach space, then this whole space, remember it's a new linear space, with that norm is a Banach space. Consequently, one of the easiest things that we can conclude from this, a little corollary, if you will, is that the dual space X prime to any normed space is always going to be complete. The dual space X prime to any norm space is always complete. Why is that true? Well, you have to think about what is the dual space. The dual space is the set of all bounded linear mappings between X and R. And this guy here, R, that's the first Hilbert space, the first Banach space that we ever encountered. We figured out early on that Cauchy sequences are convergent in R under any norm we wanted. And so, well, of course, the main norm, of course, is the absolute value norm. And so this guy is a Banach space. And so the whole thing under the induced norm, the operator norm here, is a Banach space. Okay, because R is. Now, X we don't care about. X could be anything. It's any normed linear space that we could choose. So for example, I could choose X to be, so the usual way to do it is I tell you how to choose X and how to choose the norm on X. And that tells you everything about the space. So let's take C to be the continuous functions over the closure of omega paired with the L2 norm. So we said this is not a Hilbert space or Banach space. It's not complete. However, I can still use that in this construction, okay, as my X space right here. And as long as I pair this with a Y for my range space, then this space is always going to be complete. It's always going to be a Banach space. Okay. All right. Let's look at a finite dimensional example here. Suppose that M and N are positive integers. The space of matrices having M rows and N columns can be identified with this space, the space of linear mappings, bounded linear mappings from Rm into Rn. We've talked about this a lot. For example, the prolongation and the restriction operators. These are non-square matrices which map, the spaces uh, of functions from one grid to another, right? And so we encounter matrices all the time. It just so happens that this space can always be identified with a space of matrices. Okay, so if I pull any object out of this space, then there's a way I can identify that through a certain construction, through what's called the basis construction, with a matrix. And so that's what I mean by the identification. Now, what is the way that matrix maps vectors to other vectors? Well, it's through the action of matrix vector multiplication. All right. Now we can endow Rm and Rmn with the Euclidean norm. Okay, so but we can put any norm we really want on there, so it doesn't matter. So this space, the space of matrices, is normed with the induced or operator norm that we can construct according to this prescription here, because I told you how to put a norm on the various space base X and Y. All right, that just becomes the usual operator norm or the induced norm for the matrix. And so we easily see that the space of matrices is a Banach space with those norms, okay, or with that operator norm. What about the dual space? How do we characterize that for Rn? Well, the dual space for Rn is actually and can be actually identified with Rn itself. So it's easy to show that if f is any continuous linear functional on Rn, then it can be uniquely written in the following way. F of u is equal to v transpose times u. That's a pretty cool fact, that any linear functional can be written as an inner product. Okay, so this is the case where, this is the dual space of Rn. So the set of all continuous linear functionals on Rn can always be written in this way. So this relates to something we call the Riesz representation theorem, which we'll talk about in a minute. And this says that this V really is basically characterizing F in all ways. It's it's a it's a complete characterization of F. We don't need to know anything more about F because V contains everything about it. And so, well, how would you find this V? How would I find this V? Well, I might start out by saying, well, okay, Rn has a basis. Let's think about how F maps these basis vectors. So how does F map V1? And I might, so this maps it into some real number, right? Something I'm going to call maybe C1. And I can generalize this. How does F map EI into something? Well, it always maps it to CI, right? And so now once I have this information, then I can use linearity, right? I can say, well, U is equal to the basis expansion I equals 1 to n in this case of ui times ei hat. And so I know that f of u by linearity is just going to be sum I equals 1 to n of ui and times ci, right? Well, this is just a dot product. You agree?
Dr.
This is
Wang,
just, go ahead.
in the notation, RM is in the first index, so wouldn't you go from I equals 1 to M?
So in this case, I'm just talking about the dual space of Rn. So I'm
Oh,
just talking
okay.
about mappings from Rn into R.
Okay.
Yeah. Otherwise, you would be correct. If you're talking about these spaces here, then I'd have to be saying I'm starting in Rm and I'm ending up in Rn. Correct. Well, I can just call this guy a vector C, right? So we'll call that C with a transpose and U, right? Where C is just equal to, remember, everything in our course is a column vector unless we say otherwise. And this works out to be Cn, right? So there it is. In just a couple of lines, you see that we've made this characterization true. So every continuous linear functional on Rn, remember, continuous linear functional maps into R, can be uniquely written as an inner product. So the following examples show that in infinite dimensions, things can become a little more delicate and we have to be and take more care. So let's consider the following spaces. So I'm going to take for my x C1. C1 functions on the closed interval 0 to 1. And for the norm on that space, let's take the L infinity norm. Okay, so these are functions which are continuous, functions that are differentiable and have a continuous derivative function. So these are the space of continuously differentiable functions. I'm only giving them the pointwise norm L infinity. I could give them another norm, and you're probably thinking what norm you want me to give them, but I'm going to hold off doing that for the moment. For the space Y, I'm going to define this as the space of continuous functions. This is a linear space because anytime I add two continuous functions together, I get another continuous function. I can make arbitrary finite linear combinations of continuous functions and get a continuous function. And I'm going to pair that with this norm L infinity. And so this guy is a Banach space, but this one is not a Banach space, it turns out. So you can show that. Now I'm going to define a mapping, and you may have seen this if you've had functional analysis, especially if you've had functional analysis recently. So I'm going to define the mapping to be the derivative mapping. So if I'm going to take a function f and I'm going to map it to its derivative. Okay, take the function f and I'm going to map it to its derivative. Now, since differentiation is a linear process, this turns out to be a linear mapping. However, because of the way I've very carefully and craftily defined this, it turns out it's not a bounded linear mapping. It's linear, but not bounded. So let's see if we can figure out why this is true. So let's consider a family of functions, fn, which are sine 2 pi nx for any n positive integer. Now, if I take the L infinity norm of this object or these functions, I'm always going to get 1. Do you agree? Should always just get 1. But let's now consider the mapping of that under T. The mapping of Fn is the derivative of Fn, and that's 2 pi n sine 2 pi n x. Okay, so it's 2 pi n times the original function back. Now let's take the norm in the domain space. We know this guy is going to be a continuous function, right? How do we know? Because we're taking a derivative of a continuous function that has to be sorry, we're taking the derivative of a C1 function that has to be a C function, a C0 function. So that's in the Banach space Y. And what is the norm of Y? It's just the L infinity norm, same as before. So let's take the L infinity norm of this guy. Obviously, we're going to get 2 pi times n. Well, now there's no way I can map a bounded set to a bounded set. So I could take a bunch of functions like this that can form a bounded set, right? Because I have all of those functions having norm 1. But I'm going to map those to functions which have a norm which is arbitrarily large according to the value of n. And since n has no cap or limit on it, then the mapping T cannot be bounded. Okay, so I'm not mapping bounded sets to bounded sets. In fact, I'm mapping a particular bounded set to an unbounded set. The other way you could see that this is not a bounded mapping is you can negate the definition of what it means to be bounded. So that definition is from a few slides ago, and it's given here in 1. So that's the definition of a bounded linear operator. So it violates this, right? You can kind of see that here. This is going to be arbitrarily large because it's going to be n times 2 pi, where this is just going to be equal to 1. So there's no finite constant m which can control that. No finite constant m, fixed and finite, which is independent of all the v's, can control that. So T cannot be a bounded linear operator. It's linear, but not bounded. Now, if on the other hand, we consider the same mapping, but with a different domain, then this mapping may be bounded. For example, let's define for every u in C1, let's define the so-called C1 norm. That's going to be comprised of the L infinity norm of u and the L infinity norm of u prime. So is this a good norm? It turns out with this norm, this space is a Banach space. With this norm, this space is a Banach space. So I'm not proving that, but I'm claiming it is true. So, and I'm urging you to consider it, or at least look it up, ask ChatGPT. So this version of X is a Banach space. And it turns out that now if I take the mapping or consider the mapping from this space into Y is the same, this mapping is going to be a bounded linear operator. And so you can check the details of that. I'm not going to go into that. But now Y is, let's at least look at what happens, what goes wrong with the first example, right? So the first example, the reason why this set of functions is no longer bounded is because when I take its norm, I no longer get a 1. That's because when I take the norm, I'm also going to get this derivative norm. This guy stays at 1 always, but this guy gets arbitrarily large. Okay, so if I want that set to be bounded, I have to bound the size of n. And if I bound the size of n, then I'm ultimately going to bound the norm of the output. So at least you can see where the previous argument breaks down. And that's not a proof that this actually turns out to be a bounded linear operator. That proof requires a few more details, right? All right, let's consider the space L2, the space of Lebesgue square integrable functions. Suppose that f is, well, so let's first fix g as an L2 function. Fix g as an L2 function. And let's consider an arbitrary function f from L2. So we're going to define a linear mapping which takes that arbitrary function and maps it to a number. So in other words, we're going to create a function L. Once we fix g, then the functional we're going to define is just going to be the L2 inner product of f against g. So we're putting f in as our input, and g is fixed. Okay, so that's the scenario we have here. F is fixed, or sorry, g is fixed, and f is the input. So once you calculate this number, you're going to get a real number, right? That's what we get when we do an inner product of L2 functions. This is a finite number, no problem. Doesn't matter what L2 functions I put in there. I'm always going to get a number out. It's going to make sense. And of course, the way to define this is just as the integral, right? F against g. So this defines, it turns out, a bounded linear functional on L2. So the question is, could we prove it in a minute? I had come prepared to do this, but let's see if we could kind of figure out how to do this. Well, I want to take the norm of TG of f for any f, right? But the norm here that I'm talking about is the absolute value. Well, this is equal to this inner product here, and let's apply the Cauchy-Schwarz inequality on that. So the Cauchy-Schwarz inequality says that this is less than or equal to the norm of f times the norm of g, right? But g is fixed, so we can choose m. So, right, we're going to choose m to be equal to the norm of g. No problem, we can do that. So this holds true for all f in L2, and this m is completely independent of f. So this is that's our constant we can use to show that this is bounded. So yeah, this is a bounded linear functional on L2. No problem. And it follows very simply by applying the Cauchy-Schwarz inequality. Okay, so that last, a couple of the last examples, I'm thinking in particular the example we had with the functionals on Rn, and then the linear functionals, the certain types of linear functionals on the Hilbert space L2, show that oftentimes linear functionals can be associated, or maybe in some cases are always associated with inner products. Okay, and so that conjures up this next definition. So let X be a Banach space, and suppose that X prime is its dual. Then the duality pairing between X and X prime is the following mapping. So dual pairing means I can take anything from X, and I can pair that with anything from X prime, okay, and I can get a number out in the end, okay? So it's the following mapping. Again, as I said, we're going to take an X and an X prime. So this means I'm going to think about it like this. I'm going to take a vector and I'm going to take a functional that acts on those vectors, and I'm going to combine them in some way together. The way it's most natural to combine them is to say, okay, well, I'm going to use f to act on u. That's just completely natural, right? Because f is a linear functional, bounded linear functional. It acts on things from x, right? And so I can use that to map into R. So the notation I'm going to give it is this notation here. This is used all the time in functional analysis. In some ways, I think it's caused a lot more confusion down the years than it's been worth. I think, well, why not just instead of defining this object, why not just say it's just f of u? But the fact that we've seen that bounded linear functionals oftentimes take the form of an inner product, well, this is kind of an inner product type of language, okay? It looks like I'm taking the inner product of something with something else. But in fact, I'm not, okay? It's just a defined piece of machinery, a defined object. F, comma, U, X prime, X. That's a real number, and that thing is a defined object. It's just equal to F of U, okay? So this becomes a little bit confusing sometimes for students, okay? What I'm doing here is I'm taking any point from the space, a vector call it, and any linear functional acting on vectors of that type, and I'm combining them together in a pairing, and of course that gives me a real number. I'm combining them in this way. And that's really what I'm defining this object as. That's the so-called dual pairing or duality pairing. Okay, so this looks like an inner product, and even though it looks like an inner product, oftentimes it is, but it isn't actually an inner product. Now, here's where the notation really came from. So if I look at that last example, we saw that the linear functional TG is defined through an inner product, and it acts on F. And so this would be, the notation would be L2 prime, the dual space of L2, and L2. Okay, so the dual space of L prime, that's this guy. He's from that space. That's the space of bounded linear functionals on L2. And this space, L2, well, this F is coming from that space. Now, how is this defined? Well, this is just defined as TG of F, right? But we realized that's just going to be the inner product from, what was it, 0 to 1. Well, actually, I'm not going to write that. Let's write it in the simplified form, which is the reason for this. This is just going to be GF L2. So oftentimes I can do this. I can make a pairing which looks like that, okay? And it ends up just being, in fact, an inner product, okay? And so that kind of gave root to this notation or this definition for this object called the duality pairing. I'll show you later on. It is a little bit of a useful notation, but it also does kind of get in its own way an awful lot of the time. So because it's confusing. So be a little bit careful about that. Go over some examples and see if you can convince yourself that this makes some sense. For Hilbert spaces, this duality pairing essentially coincides with the inner product. And so that's what I just showed here. Okay. Now, if it's not a Hilbert space, the underlying space is not Hilbert, then that may not be true. However, I can still define the duality pairing. It's just, it might not be related to an inner product. For every, or for the Hilbert spaces though, so the dual space or the dual pairing is the inner product, period. It just is. And I'll show you how in this theorem. So the Riesz representation theorem says this: let V be a Hilbert space. Okay, there's a linear isometry between V and its dual. In other words, what this is really saying in kind of understandable symbols is for every F in V prime, there exists a unique object, let's just call it an object for now, in V, such that the dual pairing is equal to the inner product of that object against U. Okay, so that's the inner product on V. Okay, for every V in F in V prime, every bounded linear functional, there exists a unique representer. That's where the representation theorem comes from, a unique representer. And the fact that it's unique is what's defining the isometry here. There is a unique representer in V such that the dual pairing is just equal to the inner product. Another way of saying this is that the action of F on U, which is equal to the dual pairing, is just equal to the inner product of the representer against U. Okay, this is the Riesz representation theorem. The second part of Riesz representation is that the well, I guess this defines the one-to-oneness. The isometry part comes from the fact that the metrics are the same or the object norms in exactly the same way. Um, uh, to be honest, I always confuse these terms, but I think, well, at least for me, they're confusing. Let me just leave it at that. Okay, so the norm of that object in V is exactly equal to the operator norm of F. The norm of the representer in V is exactly equal to the operator norm of the original F. So that's the punchline of the Riesz representation theorem. It's the second punchline. Okay, there are two. Now, this object here is what we call the Riesz map. So the Riesz map, this object here of theorem 11 is called the canonical Riesz map. And it's clear from, if it's clear from the context, we're going to drop this subindex V. So if it's understood that we're working with L2 all the time, then there's no reason to carry around this L2. Now, why is this? So this takes a little bit of proving before you can accept it, I think. The first thing is, well, it wasn't clear at all, that this defines a mapping. Secondly, it wasn't clear that it's a linear mapping. And third, it wasn't clear that it's a bounded linear mapping. So let me show you that it's all three of those things, okay? That it's actually a linear map, that it's actually a mapping, that it's actually a linear mapping, and that it's actually a bounded linear mapping. So those 3 points. Well, why is it a mapping? Well, because for every F, there exists a new object, a unique object in V. For every V, F and V prime, there is a new object. So we can think about it like this. RV takes a functional and maps it one-to-one and onto an object in V. So that's the mapping sense. That's the sense in which it's a mapping and it's one-to-one. Well, let's see. I'm proving that it's one-to-one. Am I proving that it's also onto? Well, the proof that it's onto is that any object that you want will generate a bounded linear functional through the operation of or through the action of the inner product. So that's what gives you the onto-ness. So this uniqueness here gives you the one-to-oneness. Okay, so it is a mapping, so that takes care of the first part. The next part is it a linear mapping? Well, we know, let's use two different functionals. So f of u is equal to the Riesz map of f against u. Actually, we know it's the inner product in the space V. And let's take another one, G. And we don't have to use U, we can use G of V, right? V might be confusing. Let's use W. Riesz map F, W. Okay. So now let's combine these two things together. What if I were to, what do I need to show, right? So the Riesz map, we said, takes bounded linear functionals and maps them to objects. So we want to show that it's linear. How do we show that it's linear? Well, we need to show that Riesz map of, let's say, alpha f of u, or let's just do it like this, alpha f plus g equals alpha times the Riesz map of f plus the Riesz map of G. So that's what we need to show, right? Let's put that up here. Well, how do we show that? Well, let's just take we know that these two things hold and these objects are unique. I got that wrong, right? So this should have been a G here. Right? Okay, so how do we show this? We'll put a question mark there. Right? Well, um, let's take the let's take this object here and consider what it is. Well, if we take this is actually almost a tautology, right? If I take this for every u, what do I know happens? Well, I know that this one's going to be alpha r v f u, and this one's going to be resmap g u v, right? But now I know that this object here is an inner product. It's linear in both its first and second inputs. And so I can write this as alpha RVF plus RVG against U V. And now we know that the Riesz representation theorem says that, well, this is a linear functional, and I found a representer, but I know representers have to be unique. So that means that this guy is the representer. That is equal to the representer of that new bounded linear functional. Therefore, this is true. And so that's the proof that it's linear functional. Now, what about boundedness? Well, boundedness just says I need to show that something like, let's revert back to black. So for boundedness, I need to show what? I need to show that RV of some, actually any f, is less than some constant times, so let me think about this. That's taking that. Right. Right? I have to show that. But actually, I know that this guy is exactly equal to the operator norm of f. So actually, I don't get this with an inequality, I get it with an equality, and the constant is exactly equal to 1. All right. So in other words, the boundedness constant for this case is just m equals 1. So I'm done. That shows that everything stated here, which was brushed under the rug, right? So there's a lot of details there that I'm skipping over, and I'm assuming that you guys have seen in one shape or form before. I know a lot of you have taken applied linear analysis. I know a lot of you have taken functional analysis, and some of you have seen this in a good course on in 447 or 448. Whenever I taught 447 and 448, I actually reviewed some of this stuff a long time ago. All right, the next concept I need to review is something called weak convergence. And if there's a weak convergence, that probably means there's a strong convergence, right? And the strong convergence is just the usual norm convergence. Remember, what does it mean to converge in norm? It means that, so if I have a Banach space X and a norm associated to that, then Vn converges to V if Vn minus V in X goes to 0 as n goes to infinity, right? That's the norm convergence, and that's what we call the strong convergence. So we also have something called weak convergence, it turns out. Well, because I've just said it, it's true. And the weak convergence is defined this way. So let X be a Banach space, and suppose that x prime is its dual, we say that the sequence Vn in x converges weakly to a point V in x, okay? If and only if the limit as n goes to infinity, what is this object here? Remember, this object here means the dual pairing. So if you don't like that notation, just just uh, rewrite it as Vn minus V. So I'm often doing this myself whenever I see something like this in a book. But people, analysts love their dual pairing. Uh, I think it's confusing a lot of times, but it's not hard to reinterpret it. But okay, so this object here means that. So this linear functional, right, acting on Vn minus V is equal to 0 as I take the limit, right? The limit as n goes to infinity of f of Vn minus V is equal to 0. But this has to hold for every f in the dual space. That's the only way that you can get this thing called weak convergence. It has to hold for every um, functional in the dual space. So here's a neat little fact. So strong convergence automatically implies weak convergence. So let's see if we can prove this. Strong convergence implies weak convergence. How do we show this? Well, we want to show that this guy is going to get small eventually. So let's use what we know. If f is a bounded linear functional, then what do we know? What do we know? So if f is a bounded linear functional, so let's think about that, then f of Vn minus V, it's bounded, right? So that's less than some constant m, which only depends on f, right? The m constant depends on f, and then this is going to be Vn minus V, and that's measured in x, the x norm. Well, I know that this, since I'm assuming strong convergence, I know that that guy goes to 0, right? So all I have to do is fix f, fix f. So maybe we'll start by writing our proof like that. Fix f, then, well, where are we fixing f? F is a bounded linear functional, right? And if I fix f, that means that this m becomes fixed. And so for every fixed f, this isn't getting bad, right? But this guy is going to 0, so that means that this guy goes to 0. So that says that that limit has to be 0 for every f. Okay, so simple proof. Strong convergence implies weak convergence. The other way around is not true. Weak convergence does not imply strong convergence. You need something else if you want to get strong convergence. There is another little simple thing that if I have weak plus this other little simple thing, then you get convergence. And it's escaping my brain at the moment what it is, so I'm not going to try to guess. So some of you who are taking functional analysis now, you probably know this. All right, so here's an example of weak convergence. So let's see, this one's a rather lengthy example. So let's see, I might be able to get through it. I'll run through it and then we'll start here next time as well. So let's consider this sequence of functions in L2 from minus pi to pi, defined by Vn equals sine of nx. So this is a sequence, perfectly good sequence of L2 functions. So let's show that this sequence is not convergent in a norm. Well, the easiest way to show that this sequence is not converging is just to show that if I take the Cauchy difference between two functions, I get something in norm which is not converging to zero. So in particular, if I take the Cauchy difference of Vm minus Vn in the L2 norm squared, I get 2 pi, always, as long as m and n are not equal to each other. All right, so that shows that the sequence can't be Cauchy, and if it's not Cauchy, then it doesn't converge. And the reason that's true is because, well, I'm in a Hilbert space. So if it were Cauchy, it would converge. If it's not Cauchy, then it definitely doesn't converge because Cauchy and convergence are equivalent in a Hilbert space. But this sequence does converge weakly, as we're about to show. So we're going to show that Vn converges weakly to zero, which is a weird thing. It's a weird thing because these guys are just oscillating faster and faster. Why is it converging to zero? The reason is because it's converging in some sort of average sense to zero. All the wiggles are kind of getting this function closer to zero. So to obtain this, we're going to invoke the Riesz representation theorem, which says that any bounded linear functional on L2 is actually an inner product. Okay, so really all we have to do is show that if we put that sequence Vn in the inner product with any f that's L2 and show that this goes to zero, then we'll show it. So we're just going to let f be an L2 function. Okay, fix that guy. And so all we need to do is show that this integral, whenever I put Vn in here, goes to zero as n goes to zero. That'll suffice to prove it. Okay. So, well, how do I do this? Well, if f is a fixed L2 function, we're going to use the fact that step functions are dense in L2. All right. So a step function in this case, for our setting, is just a function that looks like this. Okay, we have an interval from minus pi to pi, and step function looks like that. Okay, you just need a partition, and the partition is given by these numbers ci, I equals 0 to m, and they're arranged in increasing order, right? So this is we're claiming that all functions like this are dense. So I can get arbitrarily close to f in the L2 norm with a function which looks like this, okay? So-called step function. So I'm going to define an approximation of f, which is just this step function like that. So a step function like that is given by these values ai. So starting with 1, it goes a1, a2, a3, a4, etc. And this is going to be multiplied by a characteristic function on that half open interval ci minus 1 to ci. All right. So I'm going to have to stop there. I shouldn't have even embarked on this, but what we're going to do is use something called the Riemann-Lebesgue lemma and use the fact that we can approximate f arbitrarily well with these step functions, use the Riemann-Lebesgue lemma. Actually, we'll prove the Riemann-Lebesgue lemma, and or you can quote it if you know it, and then show that essentially if I put Vn in here, this limit as n goes to infinity is always going to have to be equal to zero, following from this fact, the step function density and the Riemann-Lebesgue lemma. So I'll stop there and take any questions that you guys have.